Hello everyone, I'm Sunggun. In this video, I'm going to talk about PC update stage of y86 sequential processor implementation. Okay, this is the last tutorial of the TOM project, so we are happy to finish all the modules. Good, let's get started. Here we have a figure of PC update stage, and this is figure 4.31 in the Bryant book. And let's see what it does. Okay. First, it takes three data inputs: val C, val M, val P, and outputs. And actually, it selects one of these three data inputs, and then and it is actually next PC value. And this selection is based on control signal I code and what's condition signal. Okay, this is 1-bit signal from the execution unit. And let's see each data and recall that where it comes from. So val P is generated by fetch unit, and it is actually PC plus length of current instruction. Okay, so we use this PC value for the next PC value so far. Okay, because we don't have any other candidates. Okay, but since we implemented all the modules stages, now we have two more candidates, which is val C and val M. Okay, so val M is value from the memory, data memory, and in which case we the memory stores instruction address for the next PC. Okay, when program has a call and return instruction. Okay, so when call instruction is executed, then it stores the next return address to the memory. And when return instruction is executed, it restores the return address and then use that as a next PC value. Okay, so val M is also another candidate in case we use call and return instruction. Okay, but we don't use for val C. Okay, in which case val C could be next PC. So if the current instruction is jump instruction, then and jump instruction stores the destination address in the machine code, which is val C. Okay, so this is for jump instruction. Let me rewrite like y86, and then this is for call and return instruction. And then all the others we use val P instructions. Val P as the next PC. Okay, that's it. Okay. So in summary, let's see this pseudocode. So as we know, we don't implement call and return instruction. So let's ignore first and third one. So for if the instruction code is jump, the second case, and condition signal is true, which means we need to jump, right? Then we select val C. Okay, remember that we should jump only if condition is true. Otherwise, we select val P. Okay, that if a condition is not true, then it will fall into this case, val P. Yeah, again, for if I code is some other instructions, not call, not jump, not return, then we select val P as a next PC value. Okay, good. Yeah, this is it. But the problem is we don't have condition module, the module that generates condition signal actually. Yeah, I didn't mention about it in the tutorial of execution unit. So we need to figure out how to implement condition unit now. Okay, that I intentionally deleted until we talk about what's that PC update state. Okay, we have a condition module in the execution unit. Okay, again, let's see what it does. So it takes instruction function code because we are dealing with conditional instructions. And it takes condition code, and then it outputs 1-bit signal whether to jump or not. Okay, if this processor executes jump instructions, one of the jump instructions. But this condition signal also is used by conditional move instruction. So if this signal is true, then the instruction actually move the data to the destination. But otherwise, condition signal is not true, then jump is not happening, and conditional move actually does not move the data to the destination. Okay. Then how do we decide this condition signal? Okay. But we just know it is based on instruction function and condition code. But yeah, we are fine. We have a reference, which is figure 3.12. Okay, here we have many jump instructions, but no worries. It is actually a figure for x86, but we can use it because y86 is the subset of x86. Okay, so then we can just take instructions y86 supports. What are they? JE, JNE, and JG, JGE, JL, JLE jump instructions are supported by y86. Okay, then for each jump instruction, so we figure out which jump instruction we are executing using this I function. Then if for each jump instruction, how do we make a correct condition signal? It is based on jump condition here. Okay. So if we execute JE instruction, for example, we this condition module evaluate this equation, just a simple zero flag. Then if it is true, then it outputs 1. If it is not true, it outputs 0. Okay. So for another example, if this processor executes JNE, then it evaluates this equation, not ZF, 0 flag. If this equation is true, then it generates 1, otherwise 0. Same goes for the other instructions. Okay, done. So then we know how to implement condition module. Okay, you can refer to this table to implement this condition module. But another problem is I didn't mention, or we didn't talk about something detailed, how to generate condition code inside ALU. Okay, we should have a correct generation logic for condition for each condition code, ZF, SF, OF. Okay, so let's talk about it in the next slide. So we have 3 condition codes: flag, 0, sign, and overflow flag here. So first 2 flags are quite straightforward. Okay, so 0 flag is set if the most recent OPL instruction computed 0 value. Okay, So in other words, it will be set if value E equals to 0. Simple. And for a sign flag, so it is set if the most recent OPL instruction computed a negative value. Okay, then how do we know the negative value of negative value? We can look at the most significant bit of value E. Okay, so yeah, again, it is set if MSB of value E equals to 1. It is quite straightforward, but overflow is a little challenging. Actually, you need some more understanding of two's complement and some more ability to make digital logic for this overflow detection. Okay, so let's see the definition of overflow first. So it is set if the most in recent OPL caused a two's complement overflow, either negative or positive. Then what is two's complement overflow? Okay, so I'm not going to cover details of this concept. So you can go to this YouTube video and watch. I think this is good tutorial video. But I already summarized for you to implement this code like overflow detection logic. But the thing is, this detection logic is different for different operation. Okay, so what kind of operations we have in the ALU unit? So we have add, sub, and XOR. Okay, so but good thing is the AND and XOR operation cannot make overflow, so we don't need logic for these two operations. But add can make an overflow, and also sub can make an overflow. Okay, either negative and positive overflows. So each detection logic is different, and each overflow detection logic is different. But so here we have a Boolean equation for both add and sub. I mean, for detecting this overflow here. So overflow is 1, or overflow flag is set if this Boolean equation is true. Okay, then let's try to understand this Boolean equation. So in this equation, we have 3 variables: val A, val B, val E. And we know what they are. And we have a subscription n minus 1. So where n is the data width. So what is the data width? It is 32. We are using 32-bit data line, and it minus 1. This is 31. Okay. So then ALU A31 means the 32nd bit of ALU value ALU. Okay, so which is actually MSB of ALU, right? Then if the ALU B31 is the most significant bit of ALU B, val E31 is the most significant bit of value E. Okay, then each variable has 1 bit data. Okay, then finally we can understand this equation. Okay, so let me just roughly read this equation. So this bit and this bit and this bit first, and then until here is the detection logic for add. or this bit, not of this bit, and not of this bit, and this bit, which is the detection logic for sub. Okay, so if finally the overflow flag is set if detection logic for add is true or detection logic for sub is true. Okay, then we are done. So once you can implement this Boolean equation, then you have a correct logic for condition code generation completely in the ALE unit. Okay, yeah, we are done. So I make a tutorial for all the processor stages from the fetch unit, decoding unit, execution unit, memory unit, write back unit, and what PC update unit, okay, stages. So now we just put it all together and then run it. Okay. Okay, good job, guys. And in the last video, maybe not last video. So in the next video, I'm going to demonstrate a PC update stage. Okay. Bye.